So good morning, everyone. I welcome you live and on paper for our special CatLab lecture. We are very pleased to have today Professor Graham Hutchings with us. It is fair to say that he is one of the world-leading scientists in catalysis, and he has shaped, I think, the science of catalysis in the last 20 years in the whole world quite significantly. So we are very pleased that he is here, and you will understand very quickly why he did this. I give you a few words on where he comes from and what he is doing. If you look into his CV on the homepage, then you better don't think you would want to read this out here, because it is extremely long and extremely detailed, and only the list of awards and prizes is more than 1 page long, so I will not do that. I will give you a short idea. So Graham Hutchings started at the University College of London, and he studied biological chemistry, but then he decided maybe that was too lively, so he went into petrochemistry, which is the old part of biological chemistry, and he worked for ICI in various functions quite a while, and he got a lot of management skills there, but he also gave it back to the company because he took quite a few responsibilities in ICI. These responsibilities brought him also to South Africa, and ever since he has a very strong and vivid relation to South Africa. He worked there also as university professor, so one can clearly see strong links, strong ties. And then he decided to come back to UK in 1987, and that was also the time when we got to know each other, to Liverpool. Those who are experts in catalysis, they know Liverpool is an important place there. Leverhulme Center, I think, is very well known still today. Bridging surface science and catalysis, and Graham Hutchings made it there to, I think, the deputy director or the co-director, I don't know exactly, with Eric Deron, so it's not so important, but he made it up there. And then he decided, maybe that is also not exactly what I want. So he decided, I need to shape a university, and the university that had the pleasure that Graham was about to shape was University of Cardiff. And I think he made it there into all ranks, including vice president for research and everything. But most importantly, he really shaped there the catalysis science. In the UK catalysis science wouldn't exist without Graham. The UK catalysis hub is you, and yeah, it is you, and a few people who work with you, but essentially it is him. So you can say he organized anything and everything that is necessary to do catalysis. A few words on what he's doing scientifically. He did many different things, so oxides, VPO, you name it, but he's most known for the combination of gold and palladium. And he did essentially anything and everything that we can do with gold. And if gold is not fun enough, then he adds a little bit of palladium, and the combination of gold and palladium is extremely useful. And we will see it's probably also in his presentation. And when you have these two elements, you can work on many different reactions that are relevant and important. And so Graham is one of the people who really try to understand the function or the concepts behind catalytic processes, and then he uses many different reactions in order to make practical use out of this. And the practical uses, methanol synthesis is a very important reaction, H2O2 synthesis, oxidation of alcohols. Yeah, you will do this much better. And these days, acetylene chemistry, that is also something that brings us together here in CatLab. And with this, I would like to leave the introduction, and the floor is yours.
Robert, thank you. Thank you very much. And it's a really great pleasure to be here with you in Berlin. It's a city I always like to visit. I haven't been to Aldershof, I was trying to say to Cassia earlier today, probably for 30 years. So this part of Berlin I haven't been to for a long time, but I've been coming to the Fritz, which is where Robert was, for probably the last 20 years at least. So I have a strong association and love for Berlin and the science in Berlin. I don't think it's fair to say I am UK Catalysis. I mean, UK Catalysis Hub was Richard Catlow and myself who really started it, okay? So I've got to give, seeing as this is being streamed and Richard might be watching, I can't say, you know, I've got to let know that Richard is also one of the main drivers. But it's now for the younger people to take over, is what been saying. So what will I talk about today? Well, okay, gold and gold alloys. Where do I point this to make it work? We should have checked this beforehand. It was checked beforehand. It's me. Yes, perfect. It was one click away. Right, so what I'm going to talk about is gold catalysis, and I want to talk about CO oxidation, because that's, to some people, where gold catalysis started. Acetylene hydrochlorination, a reaction which I very much enjoy working on, and methane oxidation, which is more recent. And then I'm going to talk about gold-palladium catalysis, alcohol oxidation, coupling chemocatalysts with enzymes, and water disinfection. So the last two are taking catalysis into new areas and new directions. And the first four are the more traditional way of thinking about catalysis, the way in which I view catalysis. So let's think about pre-gold catalysis, go back to 1980s. If you wanted to write a grant application in 1980 and say you were going to use gold as a catalyst, all the referees would say it's not going to work. This is just fantasy. And yet you look around the periodic table, around gold here, there's a nice gold nugget. You've got platinum, palladium, silver. These are all used as catalysts in nanoparticulate form. But the conception, the perception was that gold, you wouldn't be able to make stable, small gold nanoparticles. They would always sinter very rapidly. And so people didn't really try. But people did. I mean, Jeff Bond did some work on small gold nanoparticles back in the early 1980s and showed that you could get an EPR signal with them, and you could do some very interesting catalysis. But gold at that stage was never the best catalyst for a reaction, and that's the step forward that was subsequently made. So there was a sort of perception that gold wouldn't work at all, and that was overtaken really by, and I wanted to show this slide. This is Masataki Haruta. He sadly died earlier this year, died far too young, at the age of 74. A very good friend, and a good friend for gold catalysis. And he showed in his paper, this is published paper in Journal of Catalysis in 1989. It's the second paper he published on the subject. This paper has been cited over 4,000 times. If you ever want to write a paper as a young scientist, this is the type of paper you want to write, because it is really a seminal paper. And he showed in the paper that you could make a catalyst with gold and iron oxide, with 5% gold. It's a lot of gold. You don't want to use that amount of gold. By co-precipitation. And at 400 degrees calcined, this material was active at minus 75 degrees, which is around the coldest temperature on the planet. So this really is sort of ambient temperature wherever you are in the globe, CO oxidation. And if you made it by impregnation, and it's curve 7, and gold powder is up here. So this is the temperature, and he really perfected this low temperature activation of CO. But when he published it, if you read this paper, the method is not described as clearly as it perhaps should be. Now, this is classic with catalyst preparations, unfortunately. Any of us in the literature, you want to make sure you define everything when you describe a catalyst preparation. It's crucial. But it just describes it as a co-precipitation method, really. And people couldn't reproduce it. And that was a real problem. You've got a paper that's a headline paper, and all of a sudden, nobody can reproduce it around the world. But Masataki traveled around the world showing exactly how he made it. And I'll show you in a minute. And it's totally different from the way you think co-precipitation should be done. And that was the problem. So we wanted to know, working with Masataki, what was the active species in a gold catalyst. Now, this is a stem, AC stem micrograph. You can see the 1 nanometer spacebar here. of a gold iron oxide catalyst made by co-precipitation, but made by co-precipitation the way I would make a catalyst by co-precipitation. So this isn't the active species, really. And you can see there's gold atoms on here, maybe dimers, clusters, small nanoparticles, bigger nanoparticles, bigger nanoparticles. And so there's a whole range of structures there. And for about 20 years, people asked the question, well, which one of these is active? And there's a lot of debate in the literature on this. And so we put a little team together working with Masataki, both Jenny Edwards and Simon Freakley. These were students, then postdocs, spent time in Masataki's labs, and Chris Kiley and Kian Hay did the microscopy. And we set about this, and we were surprised, really, to learn what the real preparation method was. And it's totally different from what I thought it was. I'd never had discussion with Masataki before this, so we did it our way. And so the T series is Tokyo, and the C series is Cardiff. And so the way we made it is you take the base and you put it into the acid. And that is a normal way in which you would do the titration. And you do it slowly, because this is an exothermic reaction. You don't want it to be on the ceiling. Masataki does it the other way around, or did it the other way around, and he did it in one go. Basically, you have your two beakers, and you just, with one solution in one and one in the other, whoomph. Now, you can't make large quantities of catalyst that way, but you can make enough to do the tests that you want to do. So these two very different methods, and then you recover it by filtration, dry it, and then calcine it, this time at 300 degrees. And when we looked at these, this is the data that was done in the Tokyo laboratory. The two catalysts that are dried at 120 give almost identical activity. But when you calcine the Cardiff one, it gets worse. When you calcine the Tokyo one, it gets better. The reason for that is this rapid co-precipitation encapsulates gold inside the iron oxide crystallites. And when you heat it up, that gold comes to the surface of the iron oxide. So there's a reservoir of gold within the nanoparticles of iron oxide. Whereas the Cardiff one, that doesn't happen, because you're doing it slowly, the gold is on the outside, there is no reservoir, it just sinters and it gets worse. So that explains the catalytic activity. And we thought, well, naively, that these two, because they've got identical activity, they will have identical distributions of active species. It's a naive thought, and we were very wrong. They are totally, you can't see the same. And Kian Hay, the PhD student, must have taken about 1,000 micrographs. And you could scatter them all over the floor and say, well, which one is which, and you can't. And it turns out there is not one magic active species in this catalyst. There is a hierarchy of activity. The atoms have got a little bit of activity. It's the clusters which have got the most activity, and then the nanoparticles. So it's clusters, nanoparticles, atoms. And the actual activity you've got is a sum of the distribution of those. So if you've got lots of atoms, it's not going to be a particularly active catalyst. Lots of clusters, yes, it will be. But they've all got some activity. So it's a hierarchy of activity. So the summary of this is that, hang on, shouldn't have pressed that one. It's gold. It's got to be on a reducible oxide. Defects are very important in this chemistry. I'm not going to go into happy to discuss the mechanism, but I'm not going to go into that in the lecture itself. But the activity is highly dependent on how you make the catalyst. Now, that's a standard thing. It's going to be a mantra all the way through this lecture. How you make a catalyst is very important. And you've got this hierarchy of activities of the species present. So at much the same time as Masataki was doing that, I was working on acetylene hydrochlorination. But it's a much more difficult reaction to do. It's not one I recommend you get into unless you like making reactors. and having them disappear before your eyes, because HCl is very corrosive. If you have a little bit of moisture, you know, mass flow controllers, they're a consumable in this type of chemistry. Okay. It's expensive to do if you want to do it. And that's probably why not many people picked up on this chemistry for a long time. But in terms of this, the early work doesn't involve these teams. It does involve this guy here, Peter Johnson, who was one of my first PhD students at the University of Witwatersrand, and he's been involved in this story all the way through. And in Cardiff, he came to me and said, can we work on this? So this is us. This is an ACS mug here, which is a gold mug, if you might recognize that there. And we had a couple of PhD students working on this, Grazia Malta and Simon Dawson. Grazia, I think she was in like her first month of a PhD when she went to Diamond to do the initial experiments on this, the synchrotron. And it's unusual, like the first spectrum we got in Diamond said what the active species in this catalyst was. So I think it must be one of the quickest high impact papers ever to be made. I think she'd been in the job 3 weeks, something like that. So obviously it took a lot longer to write the paper, but it was a very good start. Then Simon Dawson followed on for her. Simon Freakley was a postdoc in this. Chris Kiley was involved doing the microscopy, and Dave Morgan and Rob Jenkins were involved in making sure the spectroscopy and all the analysis was right. So before that team sort of got together, back in 1982, 1983, I was working in ANCI in South Africa. I was doing production support, I was doing research and production. And I was asked to find a better catalyst than mercury for a particular reaction, which is acetylene hydrochlorination. Now, this is a commercial reaction. It was operated in South Africa. That plant is now defunct. And the acetylene is made from coal. And this is now very well used in China. There's around over 30 million tons of VCM made every year in China using this process. And it's produced in about 90 plants. This is a sort of picture of one here. There's pairs of reactors where the first reactor does most of the conversion, and then the second reactor mops it up. So you have 100% conversion overall, but you don't do it all in one reactor. It's an extremely exothermic reaction. And the catalyst that was used until very recently is mercuric chloride on carbon. It's 10% mercuric chloride of carbon. Each of these reactors has 6 to 7 tons of catalyst. 10% of that is mercuric chloride. Exothermic reaction, the reaction taking place around 200 degrees. Mercuric chloride sublimes at lower temperature than that, so this mercuric chloride has a chromatographic effect moving down the catalyst bed. So some of the reactors reverse the flow after a few months and have the mercuric chloride going up and down in the reactor. But a lot, eventually, this mercuric chloride is lost to the environment, and it is a huge environmental problem. So every year, around 1,000 tons of mercury is lost to the environment. That's big. It's not what you want. So this is why people have been looking for an alternative catalyst. And so charged with this from an industrial point of view, I went to the library. And it's an old saying, a day in the library saves you 6 months in the laboratory. And I found a paper which had tested 30 catalysts for this reaction, different metal chlorides on carbon. And the data were presented as a correlation against the electron affinity. And it didn't look like a correlation at all. And I thought about it, and I thought, well, they're mainly divalent cations. So the standard electrode potential would be a better choice rather than the electron affinity. So 2 electron process rather than a 1 electron process. So being a sad individual on a Saturday afternoon at home, I had my own copy of the rubber book. Every chemist should have their own copy of the rubber. Of course, these days it's all available on the web, but it wasn't then. And so I could look up the standard electrode potentials, and I replotted the data, and I got this curve. And I thought, you know what? If that's right, then gold will be the best catalyst for this reaction. And so we built a reactor, we did the catalysis, and this shows that gold is the best catalyst as initial activity, and this is the standard electrode potential. And gold is the best catalyst for the reaction in terms of activity, and it's extremely selective. You don't get any sequential hydrochlorination, so you don't end up with ethane dichloride. So there's that was a nice start, and really I sort of forgot about it. Published a few papers, but it was interesting. I'd heard that I'd left the company I was working in Witwatersrand University, and I heard that they had actually tried to commercialize the catalyst. They'd made tons of it, but eventually the way we'd made the catalyst, it didn't work. It sort of stopped working after about 9 months, and that wasn't good enough. So we lost interest. And then one day, Peter Johnson, who'd been involved in that earlier work, was now working for Johnson Matthey, and Johnson Matthey had acquired the rights to the earlier ANCI work. And so he came to my office in 2007 and said, look, we really want to make a catalyst that works. So how do we do that? And the problem is that the original method uses aqua regia with 2% gold. Now, 2% gold will bankrupt you. It's too expensive, although the gold is not lost, so you can always recover the gold. It's not a problem. But ideally, you want to make a catalyst with about 0.1% gold, or even less. And you can't use aqua regia, because what we did was we had gold, and we dissolved in aqua regia and then impregnated it onto carbon. It's an excellent catalyst. It works. But you can't do that if you want to make tons of this catalyst. So you need a water method. And basically, Peter made the real key step. He said, well, look, gold is a soft center and chloride is a hard ion. So gold, chloride, chlorine bonds are weak. And so in any effective temperature, you will lose that and you'll get gold and it will sinter and lead to loss of activity. Whereas if you use sulfur, which is a soft ligand, now the gold-sulfur bond is very strong. And so you could retain that and retain the dispersion. So it's counterintuitive in a way, because sulfur is a poison for most metal catalysts, so you don't really want to make it. But this one, it works with sulfur present. So he made a catalyst using thiosulfate, gold thiosulfate, and it was a much better catalyst at lower amounts of gold than the aqua regia method. And so this was all published in JACS in 2015, along with this data, which is the pilot plant and plant data for the catalyst. So initially, there was a pilot plant, which is a single tube, 3 meters long, 50 millimeters diameter, contained 2 kilos of catalyst with 1.1% gold. And the blue line here is the activity of the catalyst in terms of acetylene conversion against the productivity, kilograms of VCM produced per kilogram of catalyst. Because industrial, you want to make VCM. This green line here is a typical mercuric chloride catalyst. So you can see you can get to around 1,000 kilos of VCM per kilo of catalyst, and then you're losing activity. So you have to stop and recharge the catalyst. This just carries on. And this was shut down and started up 80 times during that test. So it's an extremely robust catalyst. So given that, they then did the full reactor test with 790 tubes, 1.6 tons of catalyst. And you can see that the red data here is that production unit, and it overlays the blue unit. And so basically at that point, Johnson Matthey, they built a plant in China to make hundreds of tons of the catalyst. China ratified the Minamata Convention, which seeks to ban all uses of mercury globally. And I think it's next year that becomes sacrosanct. You can't use mercury for new applications, and it has to be phased out. And it became international law in 2017. So it's a nice example of fundamental catalysis changing international law. And that's not the only example, because car exhaust catalysts did that. And there will be other examples. So it shows you, though, that work in this area really can make things happen and make things happen for the better. But what's the active species? So this is where Grazia went off to Diamond. We built a little reactor here where you can put the X-ray beam through. And we had to use very dilute conditions. The earlier work, we were using 50% acetylene and, well, 49% and 51% HCl. You always have to have a slight excess of HCl, otherwise the catalyst deactivates. So we went and did the initial experiment showed that in situ, this is the catalyst, it's got the moniker of a gold chloride, and it's fully dispersed cations. There are no gold-gold bonds in this, no gold-gold interactions. Whereas ex situ, all the techniques were telling you that there was gold zero there. XPS, XRD, and also TEM. If you're really quick, before you really got the hang of how to do these AC stem experiments, you didn't see anything, and then rapidly under the electron beam, you grow nanoparticles. That is a well-known effect. So you have to be careful how you do these experiments. And if you look at the startup conditions of this, and so this is looking at the white line height, and the white line height can tell you whether it's towards gold 1 or towards gold 3. And you can see that the activity, which is the black squares here, starts off by dipping and then rising. And the startup, it goes from something which is gold 1-like to gold 3 and then back to gold 1. So gold 1 is the really active species in this. The more gold 1 you have, the more active the catalyst is. And under in situ conditions, whether you make it from aqua regia or from the thiosulfide method, you've got fully dispersed gold cations. And it's a self-healing system because gold can be redispersed in high temperatures with halides. And that's a well-known. If you want to take a gold nanoparticle, treat it with, say, methyl iodide at an elevated temperature, you will make highly dispersed gold cations. And that's been used to actually reactivate commercial gold catalysts for doing CO reactions. But if you make it with water, if you don't have either of these ligands there, you end up with gold nanoparticles, and it's an inactive catalyst. So basically, there's a lot of words on that. I'm just going to say gold's an extremely good catalyst for acetylene hydrochlorination. It's being commercialized in China at the moment. It's running in several reactors. So gradually it will take over with time. There's a lot of people interested in this at the moment. It's one of the reactions where there are far more patents being published than academic papers. So it shows you the interest is in the industrial side on this topic rather than the academic side. But as I said, there aren't many places doing this because the reactor is a disposable item. As a reactor costs tens of thousands of pounds, you have to have deep pockets to do this type of chemistry. And so the thiosulfate method is the preferred way of doing this. And I think I've told you the story. So I'll move on to something which is relatively new. This is methane oxidation with gold nanoparticles supported on ZSM5. This is the team here. There's a team in China led by Zhen Zhu, and Richard Lewis is in Cardiff. This is the microscopy team, and this is the theory team. So here's Richard Catlow, for those of you who don't know Richard. And he and I were the two that did start the UK Catalysis up. But he's also an extremely good, I should refer to him as Sir Richard Catlow. He has been knighted, so. But to me, he's Richard. And there's a lot of funding in this, but this has really been driven out of China. I was given a scholarship to spend some time in China in 2019 in Wuhan. Matter of weeks before there was a slight problem that came out of Wuhan, which we're still experiencing today, as I'm one of the few people in the audience here not wearing a mask. Makes it difficult if you're talking, I suppose. And also it involves the Max Planck Society. We've funding through there. So this is a big thing. So the experiment here, I put this up because the way to make this catalyst is very important. You're doing reactions with methane in water in this case, and if you've got any carbon impurities in the catalyst, it will make methanol and other chemicals far better than from methane. So if you've got any carbon in the catalyst, you've got a problem. You've got a false positive. You can say, oh, I've got great results. And there's lots of this in the literature. Unfortunately, people have claimed things which aren't real. It's their catalyst that's done it all. Didn't involve any of the methane. And so in this case, this is not a preparation method I would suggest you do, but it's one we've used for small amounts of catalyst. And it's deposition precipitation using chloroauric acid with the zeolite, and you use aqueous ammonia adjusted to a pH of 6. Now, the reason I would suggest you don't do this is because gold with ammonia can form explosive compounds known as gold fulminates. Check it out on Google. They're really nasty materials. They're detonators. Don't think they've ever been used commercially as detonators. They'd be very expensive detonators. It's more lead compounds that are used for that. But this is not one I recommend. So we always have to give a health warning, but it works. And then we use a standard autoclave. And water is key to this reaction. Now, there's a lot of interest in the literature at the moment with copper zeolites. And the copper zeolites for this reaction, water is a key reactant in the whole process. With the gold catalyst, it's different chemistry altogether. And so we started off by looking at the preparation procedure with the pH of this deposition precipitation. And so this gives you an idea of the sort of the products that you're making with this catalyst. The black circles here are the carbon dioxide that's being made. The blue triangles are the selectivity totally to the oxygenates that you're making. And the products that you're making are methyl hydroperoxide, methanol, and then the C2 peroxy species and acetic acid. And on a carbon number basis, this is yield in micromoles. So when you do this on a carbon number basis, there is more acetic acid being formed than methanol. So this is not really a methane to methanol process. This is methane to acetic acid and some methanol. You can decompose these peroxy species down to methanol and to acetic acid. So they add together, basically. And we tested other zeolites. This is not an easy slide to see. I do apologize. But ZSM5 was far better than zeolite Y or mordenite. And the ZSM5 with a silica aluminum ratio of about 23 gave the best of the results. And the oxygenate selectivity is around 60%. It's sort of proof of concept ideas rather than this being anywhere of interest at this stage. I would say it's of academic interest. And if you change the gold loading, 0.12 up to 1, then the more gold you put on it, the catalyst gets more active, but it also makes more CO2. We sort of focused on the 0.5% to do the subsequent studies, and this gives you the time online processes, products that you're making, and we're always making the same products along with CO2. We don't see any CO. We see CO2, but we don't see any CO. There's a reason for that. And so we then carried on, and we looked at reaction temperature. We were always doing this at 240. The catalyst was calcined at 240. But it's as active down to temperatures of 120. You can still see products. And this was with a high pressure of methane. If you decrease the pressure down to 4 or 5 bar, now you can still get sufficient methane into the water, solubilized in the water, and you can get conversions of around 4.5% with still around 60% selectivity. So by tailoring the reaction conditions, you can get some interesting chemistry to occur. So what was the active species in this? So this is we had our crack microscopists looking at this with our AC stem, which was done in Singapore at this time. And whatever we did in fresh and used catalysts, it was just nanoparticles. There were no gold atoms, there were no clusters, just nanoparticles. And when you used the catalyst, initially, it was around 8 nanometers. On first use, it went to around 14 nanometers, average particle size distribution. And the activity went down a bit, but it was stable. So on the second, third, fourth use, they're stable. You're not losing any further activity. And so it's gold nanoparticles that are the active species. And we did a lot of theoretical work on this as well to try and understand what the mechanism is, and a lot of isotopic exchange experiments, etc. So we did a lot of work on this, and that's encapsulated in this slide. And what we think is going on is on the surface of the catalyst, you've got a pool of C1 species and a pool of C2 species. If you add CO as a co-reductant into this, the activity goes right up, and you make a lot more acetic acid. And so when we did the C13 labeling experiments, if you add CO as C12, the methyl group in acetic acid has the C13 label, comes from methane, and the COOH, the carbon in that, comes from CO. So clearly, on the surface, there is an oxygenated species which reacts with the methyl and forms a pool of C2 intermediates. And this is something which is totally different to the chemistry you'll see with copper. Copper gives you methanol. It doesn't give you acetic acid. So this is totally different chemistry, totally different mechanism. And I must admit, we're still working on it, trying to find out really what is going on. So that's something we published. It was, I think it came out on the 7th of January this year. So it is quite recent. So this shows that gold, so boron, xylitol 5, that's meant to be an active catalyst. It's not a spelling mistake for inactive. So it's a stable catalyst for methane oxidation. And the activity of the catalyst is obviously dependent on how you chosen preparation method, but really the key thing is you don't want any carbon in the preparation method because we're making minuscule amounts of product. And if you do this with a standard sodium carbonate precipitation, you've got carbon in there now, and there's more. And so you've really got to be careful how you do these experiments. And unfortunately, there's a lot in the literature which have not taken that care, I suspect. So acetic acid and methanol are the major products, but acetic acid is the real major product here. So this is a system for making carbon-carbon bonds and oxygenated. I think there's some legs in this to look at it in more detail and go forward, because it simply isn't C1 chemistry. This is C1 plus C1 going to C2. Can you do other things with this? And in this case, O2 is the terminal oxidant, and you don't need a co-reductant to do this. So if we think about gold catalysis, this was part 1 of the lecture. Part 2 will be quicker, I hope. So if you look at it, CO oxidation is a hierarchy of activities of the different species you've got present. Gold on carbon for acetylene hydrochlorination, it is totally dispersed gold cations, and best would be gold 1. And this now, it's for methane oxidation, it's nanoparticles that are active. So there isn't one size fits all for this at all. You've got a different species required for different reactions. And so this sort of is an important thing to realize, and you make these in different ways to get at the most active catalyst. So, well, gold's fun, but as Robert said, add a bit of palladium to it, and to me it gets even more fun. So, that's stuck with me for a long time now. So, we've done a lot of work on this. These are some of the people that have helped with this, again, it's much the same team as it's before, and Peter Johnson in Johnson Matty has been key helpful to this. So how do we make some catalysts with gold and palladium in them? Now, it's very simple. You can do a co-impregnation, conventional wet impregnation. And you do this simply by taking some water, you dissolve the chlororic acid, the palladium chloride in it. Palladium chloride is not easy to solubilize in water. You have to add a little bit of HCl. And that always a thing is, how do you quantify that? That's crucial. You need to know how much HCl you put into it. And then you add the support, and then you dry it. Not at high temperature, low temperature. Dry it for 16 hours or more. And then you calcine that effectively to fix it for 100 degrees for 3 hours. And now you've got your supported gold palladium catalyst. And when you look at this by microscopy, most of the gold is in very large particles. So this is particle size distribution. That's a 3, 4, 5, 6, 7, 8. So you've got these small nanoparticles here, and you've got big chunks. So you think this is actually not going to work as a catalyst, but it's actually really useful, because something in here is going to be active. I'm just showing you what, you could have a hierarchy of activities. You can have gold nanoparticles, and you can have gold cations. Well, this is a way to get everything in there. So it works as a catalyst. It's not ideal, but it works. And this is one of my favorite slides, and I like this. I like this slide. So this was published a long time ago. But it set off people being interested in gold palladium catalysts. So this is where we take benzyl alcohol, neat benzyl alcohol, and we take it at 100 degrees centigrade, 2 bar oxygen pressure, and we stir it up for 10, 12 hours. And the benzyl alcohol on this gold palladium catalyst steadily converts almost totally, almost stoichiometrically, to benzaldehyde. And the selectivity is there. Gold by itself is much less active, but it will get there. And initially, it has high selectivity, but what happens on this catalyst is it makes benzyl benzoate, makes the hemiacetal, and that then gets oxidized, if you leave it a long time, to benzyl alcohol. So it's more complicated than the gold catalyst only. Palladium is much, much more active, really active. And the way we were doing these experiments is an autoclave with oxygen pressure topping up all the time. So as you removed oxygen, so you put more oxygen in. But the palladium catalyst is non-selective. It makes a lot of carbon dioxide. So this is the selectivity for that catalyst. And because it's making carbon dioxide as a gas, the oxygen is not being replenished. And so the palladium runs out of oxygen, and so its activity effectively switches off. So the gold palladium catalyst is by far the best. And yet it's got these very large nanoparticles in it. Now, something that struck us, and it took us about 5 years to figure it out, is why is benzaldehyde forming at 100 degrees and not making benzoic acid? Because if we had some, we wouldn't be allowed to on health and safety, I know, but if we had some benzaldehyde here in a watch glass with 0.2 of a bar of oxygen over it at room temperature, during this lecture it would crystallize. And you can go home and do it yourself. Well, not home, go into the lab and do it. And you see that But this is at 100 degrees with 2 bar oxygen, and you're making effectively pure benzaldehyde. And the reason is benzyl alcohol, if it's still there, acts as a radical inhibitor to the reaction that takes benzaldehyde through to benzoic acid. And that will work with any secondary alcohol. So it's quite neat that you've got this in there. And so that's why you observe this. So what was the sort of active species in that? Well, in effect, it was the large particles, but we showed that the small particles are virtually all palladium. Medium particles, roughly, getting more gold into them. And then big particles, these 40 nanometer particles, they are 95% gold. So you've got a composition range and you've got a particle size range. So it's a useful catalyst because you've got something for everything. It's a good one to test things with, but it's not ideal. So we wanted to make, we thought initially it was these little particles that we wanted to make. So you make these by solar mobilization. This is a very old way of doing things. You take your gold and your palladium solution, you put them together, stir them, you add the sodium borohydride or other reducing agents are available, and you can use those, and you get a red colloidal sol. You then put the support in, everything goes onto the support, carbon, titania, you filter it, wash it, and you dry it. But don't heat these up, keep them at low temperature. Now, you don't have any big nanoparticles, you only have small nanoparticles, and you have a reasonably tight particle size distribution. But when you measure these, looking at the gold palladium, the small particles are now mainly gold, roughly 50-50, with the bigger medium particles, and then the biggest particles are mainly palladium. That's totally the opposite from the co-impregnation method. So I just throw that out there because we've never gone back and thought, well, why is that the case? And it would be interesting to know why that is the case. So that's something for the future from our point of view, is to look at that. But it's quite interesting. 2 methods, totally different in terms of the composition variation with particle size. So you have to be very careful how you make these. Are these catalysts any good? Unfortunately, for benzyl alcohol oxidation, no. They're very active, but they're non-selective. There is another reaction that can happen with benzyl alcohol, and that is basically 2 benzyl alcohols reacting to give toluene and benzaldehyde. It appears to be an oxidation reaction. It isn't. It's a disproportionation reaction. There is no effective oxidation. And many people do this reaction in toluene, so they don't observe it. They don't know they're making the toluene. But these small palladium gold nanoparticles, very good, but they're making a lot of toluene, so it's not good. But you could use them for hydrogen peroxide direct synthesis, which is what I'm going to come on to in a second. And so you can make them in different varieties. You can make it so that the palladium's in the middle and the gold's on the outside, the gold's in the middle and the palladium's on the outside, or you can make a homogeneous alloy, depending on how you add the various reagents and how you do the reduction steps. And these are neat things to play with. And we were really hopeful that these would be able to take hydrogen plus oxygen and make hydrogen peroxide. And yeah, they do. So the figures here, not in brackets, show you that on carbon, these are very active catalysts for making hydrogen peroxide. But the figures in brackets are the activity for decomposition of hydrogen peroxide. So, no, these catalysts they're very active. They're little nanoparticles, but they're not what you want for making hydrogen peroxide or doing alcohol oxidation. So, unfortunately. So, gold-palladium alloys, they're extremely effective catalysts for these 2 reactions, but it's the larger nanoparticles that you want. There is a synergistic effect between gold and palladium, and I'll show some data later where that's clear. In terms of the benzyl alcohol oxidation, that synergistic effect was on selectivity. It with controlling the selectivity. And we can actually make a catalyst, which gold-palladium on carbon, where you can make hydrogen peroxide and you don't decompose it or hydrogenate it. So you can take this catalyst, stir it with 14 volume% hydrogen peroxide for half an hour at room temperature, and it doesn't decompose or hydrogenate the hydrogen peroxide. Now that is quite, it tells you two things. One is you can actually try and make this chemistry really work, because that's what you want. You want that 100% selectivity. The other is the sites that make hydrogen peroxide are different from the sites that decompose hydrogen peroxide. So that is a key finding. So, I should have perhaps shown this slide earlier, but I thought about it this morning and I thought, no, I'll do it in the order that I always thought I would, not change my mind at the last minute. So it's a lovely reaction. It's 100% atom efficient. Hydrogen plus oxygen makes hydrogen peroxide. It can be a nasty reaction though, because if you get it wrong, you have a very live detonation, explosion with hydrogen and oxygen. That can be a problem. And also, hydrogen peroxide, once it's made, any catalyst that makes it typically will hydrogenate it or decompose it. So, as I said, we've got now a catalyst that can make it with 100% specificity, and we can make it at rates which are required for commercialization, which is more than 100 moles of hydrogen peroxide per kilo of catalyst per hour. So those two targets are there. What we've never been able to do is to get to that 0.6 to 1% hydrogen peroxide in the initial experiment that you can then take and distill it, because that's what the indirect process does, and then it has the distillation step. The thing you can overcome that by don't isolate it, use the hydrogen peroxide in situ as it's produced. So what I want to do now is rapidly go through two possibilities for that. So the first is a huge collaboration between a group in South Africa, industrial collaboration with BASF at the time, and in Cardiff, and the person who was producing the enzyme in Spain. And so this is chemo-enzyme cascade reactions, and one of my new areas that I enjoy working in. And unspecific peroxygenases, UPOs, were first sort of isolated in 2004. And they take one of the atoms of hydrogen peroxide and insert it into a carbon-hydrogen bond. And so they will take an unfunctionalized molecule and give you an alcohol. They will do that regio and stereo specifically. So these are very neat enzymes. They don't need a cofactor. So you don't have to have, if you're using a monooxygenase, they tend to have a cofactor that will take the oxygen and make it into hydrogen peroxide, which is fed in situ through the enzyme system. So we're using, in this case, a UPO known as PADA1. It's isolated from fungi, and yeah, this is now commercially available, and you can buy this. It's not cheap, but you can buy it. And it's active in aqueous solutions. It's a heme enzyme. And you can take, say, cyclohexane and ethylbenzene, and you can make the corresponding alcohols. But you have to be careful here, because making hydrogen peroxide tends to use low temperatures, high pressure, and stirring. And using an enzyme tends to be atmospheric pressure, room temperature, maybe 37 degrees, which is room temperature in certain countries. And they tend to be shaken. And also you use buffered reaction conditions, so phosphate buffers. So there's a huge gap between having the enzyme and having the enzyme and the chemocatalyst. So could we make them work? To do this, we wanted to take the enzyme in the presence of our chemocatalyst stirred in a single pot, making oxygen, taking oxygen and hydrogen to make hydrogen peroxide in situ, giving water as the only byproduct, and then take the alkane to the alcohol. And so there was lots of things that you had to overcome. For a start, could we do this by stirring it? Because we wanted to stir this reaction. We don't want to shake it. That's not how we do our heterogeneous catalysis experiments. And so this is the enzyme with glucose oxidase, which is a classic enzyme that delivers hydrogen peroxide. It makes gluconic acid as a byproduct, and that is a problem because that eventually deactivates the enzyme. Shaking. If you stir it, you've lost some activity. But if you put the chemocatalyst in with it, it doesn't cause problems. Okay, so the enzyme will tolerate the presence of the chemocatalyst. It doesn't poison it. Can we make enough hydrogen peroxide under these buffered conditions at low temperature, low rates of stirring? And yeah, we can. We can make around 30, 25 ppm of hydrogen peroxide over a period of time. And remember, this will be being consumed by the enzyme, so this would never build up. And so we thought, well, that's close to what the enzyme actually needs, so that's going to be okay. And when you put them together, now you have the palladium, gold-palladium catalyst on TiO2 or on carbon, and yes, they work. They work. But if you only have the catalyst, it doesn't work. If you only have the enzyme, it doesn't work. You have to have the two together, and you have to have the hydrogen peroxide in air doing this. So we do these experiments above the higher explosive limit, because hydrogen is the most difficult of the reagents to dissolve in the water. So you go way up. So, you know, this explosive limit is around 76% hydrogen in air. So we go up and we bubble it through, and, you know, very low stirring rates. If you compare the chemocatalyst with the enzyme, because this is, you know, all the enzyme scientists say, well, why bother to do this? There's no point. Enzymes do it. They make hydrogen peroxide beautifully. Just put glucose in there. It makes gluconic acid hydrogen peroxide. Don't need to worry about bridging the gap. Well, the diamonds here are the chemocatalyst in the enzyme. And this spots here, the glucose oxidase system switches off after a number of hours because the gluconic acid has poisoned the system. So there is a reason why you want to do a chemocatalyst, which is only making water as a byproduct, and not an enzyme method of doing this. And if you do this over this long time, well, long time, 15 hours, the conversion increases as you expect, and the major product we see is the alcohol, a little bit of the ketone. So you're still getting, and this is what the sort of split you get is what the enzyme would be doing with glucose oxidase. Ethyl benzene, very similar. Now you're seeing a little bit more of the ketone, but now you've got chirality, and so the enzyme is still an antioselective, giving 99% selectivity to this at 98% EE. So we retain the regio and stereo specificity of the enzyme with the chemocatalyst being present. Oh. And so you can use lots of different substrates, and this works. So I think it's quite a neat possibility of putting these two catalysts together. It's something we're exploring, and we're now working on trying to do things with enzymes known as LMPOs, which recently have been found, probably in the last 15 years, to eat up cellulose and chitin and use them as a way of making sugars and oligosaccharides. And so we're trying to make this work with that. It's very early days, very, very early days. Looking promising, but very early days. So a summary of this, before I give a very short snap one on the last item, is I think we demonstrate it's possible to couple these hydrogen peroxide catalysts with enzymes. Now, it's been known that you can do that for hydrogenation reactions for many years, but it's oxidation reactions, we were the first to demonstrate this. You can maintain all the benefits of the enzyme, and the source of the hydrogen peroxide doesn't change its activity, regio and antios activity. And so, in a way, it does represent an easily scalable supply of low levels of hydrogen peroxide. And so, as I said, we did have industrial interest in this when we were doing this. This is seen as a way that you could actually do things. So it's quite neat. And this is a picture of the little reactor we initially did it in, which is just an open tube, bubbling the hydrogen peroxide in there, and you could have the catalyst in there. So it's very easy to do. So look, this is just the last snippet. I know I'm running into time problems. And so this is a team of people at Cardiff. I stuck myself on it for some reason. I must like the photo. Yeah, well, fair enough. So Richard Lewis there, Jenny Edwards, Catalysis people, Damien Murphy and Andrea Foley. They are APR spectroscopists, which is crucial for this part of the story. And we have Jean-Yves Mallard, who is very good at understanding how you kill pathogens. And then Simon Freakley is now in Bath. We work with Welsh Water, as Paul Gaskin, and our microscopists, no longer in Cardiff. One is in Lehigh, and the other one is in Singapore. So, big collaboration again. We got into this because in the UK and Europe, there is sort of water shortage problems at various times of year, especially in the UK, especially in the southeast. And yet, if you look at a domestic dwelling, all the water that comes into the house is potable water, and very strictly controlled. And then what do you do with it? You flush the toilet. Oomph, out it goes. You use a bath or shower, out it goes. All the water going out of our residence is deemed black water and is treated as sewage. But a lot of this water that's coming from various things, you could collect it off the roof, is known as grey water. And this could be recycled back to doing toilet flushing, or you could use it to do dishwashing and things like this. But it would need replumbing the whole house to be able to do this. So it's not something retrofitting would be really quite expensive. So we were interested in this grey water. Could we treat this grey water such that it could be reused? And if you look at there is a national standard of grey water, which is amazing if you think about it. You know, that someone would come up with a national standard for this, okay? And it typically should have between 10 to the 2, 10 to the 7, the total coliforms per 100 milliliters of water. Now, a coliform is a colony-forming entity, such that if you plate it onto an agar plate, these colonies will grow. So it doesn't tell you they're E. coli, they're MSA, or anything like this. It's just colony-forming agents. And in there, be 10 to the 2 to 10 to the 6 fecile coliforms. Not nice, not nice. Definitely want to kill those. But for toilet flushing, there is also a standard. You can't flush the toilet with fetal coliforms. Oh, okay, I didn't come up with the standards, but to me. So your target is to remove 10 to the 7 coliforms, coliforming agent, per 100 milliliters of water. So that's target. So we've worked on this since 2008. It's a long time, because we were working with the building industry. And of course we had the recession. So we went through lots of building companies because they went broke. And we desperately wanted to demonstrate this in a building, which we never got to do in the end because the world has changed. And what we did was we built a little lab-scale reactor. It's not easy to see in this, but there's a little tube here where the water is flowing through it, residence time of less than a minute. It's at ambient temperature around 20 degrees. It's got water, and we're using relatively high pressure hydrogen in air. For commercially, if you wanted to do this, that would have to come down to the pressure that's the outlet of a hydrogen generator. which is around 2 bar. So you can do that. And we take is what we call our initial inoculum of 10 to the 7 coliforms per mil. So it's 100 times more concentrated than what you need to knock out. And if you do that with this little reactor, using this, so if you plated this at the start, this is the agar plate you get. You push this water through our catalyst, making in situ hydrogen peroxide, and you don't get anything. You knock everything out. So this is the initial concentration. Even a blank tube with these different gases, because of the turbulence, causes some degradation, some pathogen killing. If you put the catalyst in there with CO2, hydrogen, or oxygen separately, again, you now get some pathogen killing. But if you have the hydrogen plus oxygen together, you kill everything. So you have 10 to the 7 log kill with this very simple device. If you use preformed commercial hydrogen peroxide, you only get 3 log kill. So that's 99.9. And if you have adverts here in Germany where they say it kills 99.9% of all known germs, that's rubbish, okay? That's 99.9 is not what's required by legislation, really. You need to have 5 log kill, 99.999. But it's okay for doing things in the house, but it's not where you really want to be. So what's the origin of that pathogenic kill? And this is where EPR comes in. So we did this using DMPO as the spin trapping agent, because you want to look at short-lived radical species. And if you've got palladium only in the catalyst, there are no radicals in solution. Whereas if you've got gold put into the palladium, now the radicals are released into solution. And that was a key observation. And it's this flux of radicals in solution that is carrying out the pathogenic kill. Really high pathogenic ability. So this is different. Gold, this is 1% gold, 1% palladium, and these are different things. This is the 50-50. The red bars are the log 10 kills. And so the 50-50 is giving you the best. The black here, the black squares, they're the amount of hydrogen peroxide that's being produced. So there's no correlation really between, you can see a small amount, but it is not. There's a lot of hydrogen peroxide there being produced by this catalyst, but it's the 50-50 that is doing the kill. So it's this high flux of radicals that's doing the killing. So we demonstrate here that it's possible to couple this hydrogen peroxide synthesis and use it for water disinfection. So it's a totally new idea. And you could use this in remote areas where you just need electricity to generate the hydrogen production from a sort of typical hydrogen generator. Just need the water, where you go. So this can be used in countries where there are problems with water. Alloying gold with the palladium, it releases this really pathogenic reactive oxygen species into the water. And this method is 10 to the 7 times better than chlorination or using commercial hydrogen peroxide. So this really is neat. But we've only demonstrated it with a little bit of catalyst in a tube flowing a little bit of water. So the next stage is to see, can we scale this up and do something that will be very interesting. There was a competition in the UK recently. They take a sort of a tax on people's water bills to do interesting things. And so we put this in thinking we might actually get some help to take this forward. No. They only actually wanted to put money into things which are at technology readiness levels 8 and 9, which means they're all there, you know. So they only wanted to bank on winners. So somehow we have to convince people that this is at TRL 4, but you've got to get across that gap, which is well known. So my overall reflections are, well, I think I've demonstrated that catalyst preparation methods are very important. You can easily make very bad catalysts, but if you get it right, you can make some really good catalysts. Active sites can vary and they're reaction specific. Gold is an active catalyst. You can have it as cations, clusters, or nanoparticles for specific reaction. You can put chemocatalysts and enzymes together, and you can use catalysts in new areas such as water disinfection, and there are lots of others you can think of. So we're moving. The Cardiff Catalysis Institute is in this part of this lovely historic building. Here is where the Vice-Chancellor, the President of the university, has his office. Around the corner is where we do our hydrogen peroxide work. When he became Vice-Chancellor, President, we gave him a tour of our laboratories, and he decided that we needed a new building, somewhere a little bit further away from him. And so we were very grateful for that. And so our new building is this one here. This is a clean room for the institute we share it with. This is our new microscopy suite here. This is as you can see, it's a mock-up. I should have, but this is now built. And on April the 1st, the university took possession of the building. We will be moving in June, July. We've got a new microscope being installed here now. So the future's bright. It's fantastic. So I've run over time. I do apologize. And I thank you once again for being here. Thank you.
Thanks so much. Of course, now you understand why I took some time reading the vita of Graham, because you see very nicely how biological chemistry and heterogeneous catalysis fit together. And you see also very nicely why it is appropriate to have Graham Hutchings here, where we do our CatLabs studies, how we synthesize on a rational way heterogeneous catalysts. You see now why. And we don't want to use aqua regia here, so it's too dangerous. Now, are there any questions from the room first, and then we get also questions from the audience?
Very shortly, you have many questions, but just
You need...
Sorry. You show very convincing that when you generate a very low concentration of hydrogen peroxide with enzyme, they work very well. However, the system is not working when you have inorganic, let me say, catalysts which are able to make epoxidation, from TS1 to many also other complexes which are active with the SAM. What is the reason? Is it a special environment inside the enzyme or other effect?
Yeah, okay. That's an interesting question. You can do epoxidation with this enzyme. Okay, we've taken styrene, and you can make styrene oxide. So the specificity is it operates around pH 6. If you try and take it out of that, it will not work. So you have to have the chemocatalyst operational in the same. You can't say, okay, the enzyme, we're just going to do it the way we want to do it for the chemocatalyst. That's not the way you can make this chemistry work. You have to make the chemocatalyst fit the enzyme chemistry, and it's very, very strict. You can do some things like you can tolerate, the enzyme can tolerate being stirred, but not very fast. So you're going to be always diffusion limited on these. So the next step from our point of view is trying to make more hydrogen peroxide. If we could, because we're hydrogen peroxide limited in this. So there is no hydrogen peroxide at the end of these experiments. It's all being consumed. And that's why the enzyme has longevity under these conditions, because you'd expect the enzyme to be degraded by hydrogen peroxide. And that happens. So I'm not sure I've answered the question in terms of the specificity of things, but if you want to do anything with an enzyme, you've got to take the enzyme conditions as what you have to work with. So you can,
It is something that you have a kind of
yeah.
Is something that you have a kind of concentration of hydrogen peroxide inside the enzyme, and for this reason.
No. The enzyme will take it. I mean, the active site is inside the enzyme, but it will take the hydrogen peroxide and use it. And there's lots of enzymes that use hydrogen peroxide, and they will all do the same thing. These peroxygenases, there's chloroperoxidases, for example. There's these ones which will degrade cellulose and chitin. They always want to take the hydrogen peroxide that's generated externally these enzymes, LMPOs, will make hydrogen peroxide from oxygen if there's no substrate present. They will then go back to doing something, and so they will make hydrogen peroxide, which causes problems for them because there's nothing that the hydrogen peroxide is being used for. But as soon as you put a substrate in there, then the chemistry takes over. So no, you want to produce a slow, steady concentration of hydrogen peroxide together with the enzyme. And then you're in diffusion-limited situations.
I dare to interfere with this discussion. Are you really sure that you want to make hydrogen peroxide, or is this HO2 radical that you want to make?
I think in this case it is hydrogen peroxide for the enzyme. For other things, I mean, we just had a paper accepted on making oxenes. So you take ammonia, oxygen, hydrogen, and cyclohexene, and you can make the cyclohexene oxene. And you can do that with very high specificity. But this is at 80 degrees in aqueous ammonia. So the pH is exceptionally high, the temperature is exceptionally high. There's no way hydrogen peroxide would survive at that. So you're making a reactive oxygen species that is doing the chemistry. So
But they would do the same with H2O2 as well, because H2O2 by itself is not an oxidant. It's a decomposition product of it.
Yeah. Well, there is the process that works with ammonia plus hydrogen peroxide plus cyclohexene. And what we've shown is you can do exactly the same, actually better, with hydrogen and oxygen using this chemocatalyst. So, yeah. So it's. But with enzymes, you don't want the reactive oxidation species because it kills them. It kills them.
More questions? Annette?
Thank you very much, Graham, for this nice overview. I have a question. Maybe I misunderstood this also. Can well be. You mentioned that in the synthesis of a catalyst, and I guess it was the catalyst for the gold in zeolites for the oxidation of methane, that you should avoid a presence of carbon. Is this correct?
Yes.
But as soon as you contact your catalyst with the substrate, with the methane, then you generate carbon. So why do you need to avoid this during synthesis?
Okay.
This I didn't understand.
No, okay. Well, your catalyst, if you make it in a classic way, and it has carbon associated with it, the amount of catalyst you put into the reaction will have a certain amount of carbon there, and it will react with the oxygen to make carbon-containing products. They could be CO2, not a problem, but often they're methanol. I think there's a classic case of an iron, I'm trying to remember, there's an iron complex, which was in the sort of late, probably 15 years ago, was published. I'm not going to give authors' names or anything. And they had this catalyst, and they showed that methane, well, what they thought they showed is that methane was being reacted to make methanol. But actually it was the catalyst that was making the methanol, and none of the product was coming from the methanol. So if we make this catalyst by methods that have carbon in them, for example, a new method is sputtering. You can put evaporation of metals, and if you're not careful, you can put a lot of carbon onto the catalyst doing that. And those catalysts are really active, they're fantastic, but it's all coming from the carbon that you've put in the preparation.
But only for a short time, then it's...
No, it goes on for quite a long time. Yeah, it's not a short, no, it masks everything. It does mask everything. So that's why if you want to do this, choose methods where there is no carbon in the catalyst.
Or be more daring and do this with isotope-labeled substrates.
Oh yeah, no, but that's what you have. Well,
what we would do.
You have to do that.
We have a question from outside. Would you please read it?
Yes, thank you very much. So we have a contribution of Gregor Koch, and he thanks you very much for the great overview. And he says he was fascinated by differences in the chemical composition of the gold-palladium nanoparticles you mentioned obtained by different synthesis routes. Can you please give a comment on the reasons for the apparently size-related different compositions, which is a very nice observation?
Yeah, it is a very nice observation. I wish I could. Thank you for the question. We don't know. I think if you don't know, it's best to say you don't know, isn't it, rather than make something up. I think we seriously don't know, and if anybody's got any ideas, I would like to discuss them, because that's two different methods of preparation, and you do end up with different size distributions and different composition distributions, but I don't know why.
We might have some ideas, we can discuss this, but
yeah, that would be good.
There are more questions.
Yeah.
Thank you for your inspiring talk. Just a question to the enzyme and the palladium gold catalyst. Wouldn't it be possible to immobilize the enzyme on some substrate and use some proximity effect of the catalyst and enzyme?
That's a very good idea, and that's where we're going. I mean, if you want to recycle these catalysts, then ideally you want to immobilize the enzyme. So yes, but we haven't done that yet, but I'm sure it's easily possible. Yeah.
So are there any more questions, be them pressing or less pressing? Comments? Oh. I think it became, hey, we have another one.
Thank you for the inspiring talk. I have a question about the finding on the gold and palladium catalysts, that the sites for making hydrogen peroxide were different from the ones that were decomposing. So what caused this difference, and can that be exploited?
Yeah. It's the sites that we think do the decomposition are the interfacial sites between the metal nanoparticle and the support. So you can take a solution of hydrogen peroxide and put the support at, say, TiO2 into it. It hardly decomposes hydrogen peroxide. If you take that same solution and you add a gold palladium or a gold sol into it, no support, it doesn't decompose the hydrogen peroxide. If you put the sol onto the TiO2, so now you've got the supported nanoparticle, and when you do that with TiO2, the nanoparticle becomes faceted, and you've got a very clear interface between the nanoparticle and the TiO2. Now it decomposes all the hydrogen peroxide very quickly. And so it's these interfacial sites which we think are the ones which do the decomposition. So those you have to knock out somehow. And we found two ways of doing that. So we can make catalysts there, that's not a problem. But there's the interfacial sites. Thank you.
Again, that was a very nice explanation of why we want to do thin film catalysis. That's a very nice way of avoiding this. Axel?
Yeah, thank you, Graham, for your talk. And I have a question related to the last question. You mentioned about the metal support interaction, which plays a role here. So it's known that in catalysis on gold particles, you have, in the case of a reductional support, and a movement of the support on the particle. Do you expect something also in the system you described? Or have you indication that something like this happens?
Yeah, you're spot on, Axel. I didn't go with there is a palladium tin system where this is crucial. So you can make palladium nanoparticles on tin oxide, and then as you calcine them, the tin oxide grows over the nanoparticles. And then when you reduce them again, the palladium nanoparticles come back as palladium nanoparticles. And so if you control the amount that you grow over the surface and you take out all of the small palladium nanoparticles, it's like a tide coming in over rocks. So you want to cover up all the small rocks and leave the big rocks. And then you've got a catalyst that is extremely good at making hydrogen peroxide. And I can give you the reference to that. Yeah, it was in Science in 2017, as far as I remember, or 2016. So palladium, and it's a case of trying to grow these oxide films over it. So it's neat. You can, it's a great way of controlling. As long as you don't want the small nanoparticles, for hydrogen peroxide you don't. It's a way of controlling it. So yeah, it's an elegant way of doing this chemistry.
Are there any more comments, questions? That seems not to be the case from the outside. No, nothing more from the outside. Then there is nothing left than giving you a short remembrance, because we want to. Where is it? You bring it, please.
Oh.
Yeah.
Oh.
You bring it.
Oh. Oh, thank you very much.
So.
Oh, nice.
Yeah, it is good for you.
Yeah.
It helps. It's also good for that, but it's more fun.
Ah, more fun.
You're having
Oh,
fun.
look, it's chocolates.
Fun cut. Yeah.
Oh,
And we thought for
as long as
fun.
my wife isn't watching, Sally's not watching online, she won't know.
Okay, very good. So for fun cut, more fun is needed.
Yes.
So with this, we would like to thank Graham for being here and giving us this insightful lecture. Thanks a lot.
No, thank
and all
you.
the best.
It was my pleasure. Thank you.